Hi, welcome to Module 5 of Lecture 6. Having gone through the preliminaries and given hopefully a decent intuition for how we're going to use derivatives to find minima and maxima, we can start actually doing that. The first step is to look at the first derivative, to test the first derivative to see whether or not we have a stationary point for the reasons we just talked about in the previous module. So it's actually very simple. Having gone through all the sort of framework in the previous modules, the actual process is simple. We're going to compute the first derivative, and we're going to find all the points x star at which the first derivative is 0. As we've discussed previously, these are stationary points, and these stationary points are candidates for local minimum and local maximum. So say, until further notice, we're only considering local minima and local maxima. We're going to consider points at which the first derivative is 0, stationary points, and not points on any boundary of the space. We'll get back to boundaries again when we put all the rules together. So this is the first derivative test. In particular, this equation here is often called the first order condition. First order condition, or FOC for short. Comes up a lot. It's the first step in all minimization and maximization problems, and even when you have more than one dimension, it has a very similar character, as we'll see later on in the course. So all we do is take the first derivative, set it equal to 0. That's going to give us our first order condition. Let's try one in practice. First, a simpler one. Let's say we're looking at x squared minus 2x plus 1. Well, what's the first derivative? Again, the derivative is linear. We do each part separately using power rule. So you pull down a 2, so the first term is 2x. Second term is just 2. The 1 goes away. 2x minus 2. For the first order condition, just take a star there and set it equal to 0 and find all the values of x star that make this thing work, to make this thing equal to 0. Well, this implies 2x star equals 2, or x star equals 1. And x star equals 1 is the only stationary point of this function. That's it. All we must do is use the first derivative to compute the point at which the first derivative is 0. All such points are stationary points, and all stationary points are candidates for minima or maxima. And so taking the first order condition is our first step for trying to do minima or maxima. We can do one more example. Let's see. X cubed minus 7x plus 1. Again, I don't know if it's going to work or not, so we'll just try it out. The derivative is 3x. I'll make this a 9 actually to make my life slightly easier. 3x squared minus 9. We set that equal to 0. So this is x star squared minus 9 is going to equal to 0. We can divide through by 3 and move things around a little bit to get x star squared equals 3. Take the square root, and we get x star equals plus or minus the square root of 3. Now we have two stationary points, plus the square root of 3 and minus the square root of 3. Right? At both these points, the first derivative is 0, so both are stationary points and candidates for minimum or maximum. That is all there is to it. Take the first derivative, set that equation equal to 0, find all values of x that make that equation 0. Those are stationary points, and they're candidates for points which the function is a minimum or maximum. Note that these particular points are the points at which the function is a minimum or maximum. They're the arguments that might make the function a minimum or maximum. They're not the minimum or maximum themselves. In this case, to find the minimum or maximum, you have to plug in this into here. So you'd have, in the case of plus 3, you'd have 3 times the square root of 3 minus 9 times the square root of 3 plus 1 equals, whatever that equals, that's one candidate. The other candidate would be negative 3 square root of 3 plus 9 square root of 3 plus 1. Clearly, this one is bigger than this one, so this is probably the maximum, and this would be a minimum, but we'll get to that later. Point is, when you do this technique. You do the first order condition, you find the values of x at which the first derivative is 0. These are stationary points. To find later on potential minimum or maximum, you plug in those stationary points into the function and figure out the function's value at those points. We'll get to a more deliberate method for finding minimum or maximum very shortly. But that's it. That's the whole first order condition. There's nothing fancy. Once you can take a derivative, once you can solve an equation, you can then find the stationary points and find the candidates for minima or maxima. Note that the more complicated the derivative is, the harder it might be to find stationary points, mind you, right? But the process is always the same, right? If we had, for instance, this function over here, the derivative that we've seen before is e to the x plus x e to the x, right? That's x plus 1 e to the x would equal 0. That happens at x equals -1. Right? So various examples of this, right? Sometimes you can solve them, sometimes you can't solve them analytically and cleanly. However, the core concept remains the same. Take first derivative, solve the resulting equation when setting that equation equal to 0. That's the first order condition. Again, sets the first derivative equal to 0. Solve for all the x that make that work. Those are stationary points. That's it. And then next module, we'll go into the second derivative test to see how to specify whether or not these stationary points are in fact minima or maxima, or neither. Thank you very much.